Sorting and hashing. Today's lecture covers two of the key building blocks for query processing algorithms in a database system. And we'll start with sort. And you might ask, why would we learn about how to sort in a database system? And there's a bunch of reasons we use sorting. The first is for rendezvous, for sort of getting together tuples that need to be processed together in memory at the same time. So in the same place at the same time. That's why we call it rendezvous. One example of this is to remove duplicates, like SQL's distinct clause. We need to get all those duplicates together in some way and keep just one of them as a representative. Similarly, for summarization, like SQL's group by clause, we need to get all the members of a group together in some way and compute a summary over the members. And then finally, what we'll see is that join algorithms, particularly the sort merge join, need to rendezvous tuples from two different tables and to concatenate them together. Another reason we might need to sort is because the user asks for it. Sometimes ordering is something that's explicitly requested. So output might have to be ordered, like in an order by clause. For instance, you're used to searching the web and getting your search results ordered by relevance, by most relevant to least relevant. You certainly wouldn't want to filter through all your web search results in random order. Another reason to do ordering, which we saw in our previous homeworks and discussion, is to bulk load a tree index, like a B+ tree. Right? And so the challenge here is that we're dealing with database-sized amounts of data. So how can we sort, for example, 100 gigabytes of data with 1 gigabyte of RAM? We can't just bring the file into RAM and sort it. We have to do something more clever than that. So one question you might ask is, good, so I learned about something in operating systems class called virtual memory that makes it feel like we have a very big RAM even though we have a small RAM. Can't we use virtual memory for sorting? Unfortunately, virtual memory isn't a good choice here because it doesn't understand the algorithm we need to do. It doesn't understand that we need to do sorting. And so virtual memory is going to translate references to RAM into random disk IOs, and sorting will turn into a horrible slew of random disk IOs if we try to sort in virtual memory. I challenge you to do it. You can go ahead and allocate a really big buffer and try to sort a file. The buffer may be much larger than memory, and you'll see that your algorithm is going to be very, very slow. So we want to do something more customized, something that understands the algorithm of sorting and manages memory intelligently for that algorithm. These algorithms are often called out-of-core algorithms. So this is an old-fashioned phrase. RAM memory used to be called core memory. And so algorithms that work on data sets that are bigger than RAM are often called out-of-core algorithms. And there's two key themes to these algorithms. The first theme is single-pass streaming of data from disk through RAM, often back to disk. The second theme that we'll see is divide and conquer, where the thing we're dividing things into is a RAM-sized chunk of data that we can work on in memory. Okay, and we'll see specific examples of both of these patterns next. So let's start with the single-pass streaming pattern. And we'll take the simplest case you can imagine, which is map. That is to say, apply a function f of x for every record in a table and write out the result. If you've heard of MapReduce, this is the map part of MapReduce. And the challenge here is to do this with a minimum of RAM and to do as little I/O as we need to, so call read and write as rarely as possible. And so our approach is like this. We're going to read a chunk from the input to an input buffer in RAM, and that buffer might be a page big. And then for every item on that input buffer, we'll write f of x of that item to an output buffer. So it'll look kind of like this. We'll read in a few items into our input buffer. Let's say that's a page full of data, has 3 items on it. And we'll call f of x on each item and place the outputs into an output buffer. And you can see in this example, our function f turns rectangles into pentagons, and it makes them smaller, which is to say the output is fewer bytes than the input. So there's more room in the output buffer still for more items. And so rather than write that output buffer to disk now, we'll read another input buffer, because the input buffer is consumed. That's the second to last bullet on this slide. So we just read another chunk of data from the disk, say a page worth of data. Now we've got 3 more rectangles that we can run f of x on, and we do that, and those go into the output buffer, and we've consumed another input buffer, but there's still room in our output buffer. So we'll do it again. Read 3 more, run f of x on them, write them to the output buffer, and then we'll read another one because the input is consumed. We'll read the first thing here, we'll write it to the output buffer. Now our output buffer is full. And because it's full now, we'll write it to the output. And that way, our output I/O gets a full page worth of data for the cost of the I/O. And so you can see that the input and the output are not synchronized. We may do many inputs per output. We may do many outputs per input if, for example, the function makes objects bigger. like a decompress function, for example. Okay, but the point is that we easily adapt the rate at which we read the input to the rate at which we write the output, just based on the sizes of the input and the output. All right, and this is all done with a single thread. It's very simple, but data essentially streams through memory and never takes up more than two buffers, one for input and one for output.